Okay, this can be a little bit overwhelming, but this formula is not fully written yet. We're going to talk about it and kind of walk our way through it. But this formula is at the bottom of the front of the notes if you're following along with the notes. So here we go. We are using rectangles to find the area bound between a function and the x-axis. So here we go, squeaky marker right in the microphone. Here we go. We're going to have some function, and it's going to go from A to B, and we're going to have just some little function, and we're going to figure out the area using rectangles. So if I was using a right Riemann sum, then I would start, let's switch colors. Let's go red on this. Drop in the lid too. Actually, now's a good time for me to just sort of recap. Love that joke. Anyway, squeaky marker again. If I was doing a right Riemann sum, I would go a little bit to the right of that, and I would draw my rectangle, and then I would come up and draw my next rectangle, and then I would come up and draw my next rectangle, and then I would come up. We've done this. But what I really want, tell you what I want, what I really want, is to find the actual area using an infinite number of rectangles. Now, we're not going to go through the process, fun as it would be, but we are going to learn how to set it up and just kind of gain an understanding of what it would really mean if we wanted to use an infinite number of rectangles, which would give us the exact area. And then we're going to introduce some other notation. There's a lot of notation here that looks very overwhelming, so just hang with me for a second. We want the limit as n approaches infinity, okay, so far so good, of the sum, this is the sum, we talked about it in the last video, from 1 to infinity. Okay, we're going to start at 1, and we're going to plug in a 1 every time we see a k, and then we're going to plug in a 2, and then we're going to plug in a 3, and then we're going to plug in a 4, and then we're going to plug in a 5. And I've actually made a slight mistake here. This should say n. It should not say infinity. There we go, corrected. And so the reason it should not say infinity is because we're not going to count to infinity. We're going to count to n, but n approaches infinity, because technically I can't count to infinity, right? So that's why we have limits. So I had to make that correction. I apologize. It is correct on, yeah, it's correct on your paper. So we have the limit as n approaches infinity of the sum from 1 to n. I'm going to plug in a 1 here, figure out an answer. Plug in a 2 here, figure out an answer. Plug in a 3, figure out an answer. Plug in a 4, figure out an answer. 5, 6. I'm going to add all those answers together all the way to infinity. Takes forever, literally. But there are shortcuts to this. We're not going to go through the process. Again, this is helping us gain an understanding of the fact that the more rectangles we have, the skinnier they'll be, and the more accurate it will be when we make an approximation using a right or left Riemann sum. FYI, this is a right Riemann sum. We'll talk about it again in a minute. So, the limit as n approaches infinity of the sum from 1 to n. We're going to just keep counting, plugging in 1, 2, 3, 4, 5, 6, 7, 8 for k. And f of all this stuff, this is the rectangle height, and this guy right here is the rectangle width. So basically we're going to be finding an infinite number of rectangle areas and adding them together. Here's the height, there's the width. Now the width is delta x, and you're probably thinking, well, why is delta x in here? Well, let's talk about that. Let's talk about the structure of this. If this was a right Riemann sum, we would actually start a little bit to the right. I've drawn this in a previous video. I would start a little bit to the right of A. So I would go to A, and then I would, for my first rectangle on a right Riemann sum, I would not start at A. I would start just a little bit beyond A. How much beyond A? The width of the rectangle. Well, how wide is the rectangle? We'll deal with that in a minute. But I would go to A, and then I would go 1, start with 1, width over. And then for my next rectangle, I'd go to A and then start 2 widths over, and then 3 widths, and then 4 widths, and then 5, and I do that all the way to infinity. Rectangle height, rectangle width, what does it equal to? Okay, hold on. You're about to see something probably not seen before. Get ready. Are you ready? Let's just do it. That is a elongated S, and it represents a definite or indefinite integral. This one's going to be a definite integral. There are lessons devoted to this later. Don't let this mess you up and be like, oh, there's so much new notation. You'll get used to this one for sure. The integral from A to B f of x dx. Okay, whoa, what is all that? Do not panic about what all that is. This, my friends, is the actual area. That is the actual area. So the sum of an infinite number of rectangles squeezed in this area, squeezed in this width, would give us the actual area. And we need one more thing. We need to talk about what delta x actually is. So what is delta x? And delta x is, again, it is the width of the rectangle, but how wide is each rectangle? So for example, if I said, let's use one rectangle, well, that one rectangle would be this wide, which if you wanted to compute it actually, you would say it's b minus a. You'd be right. So it would be b minus a. I made it float for a reason. And you can see it on your paper too. So we have b minus a, but what if I wanted two rectangles? Well, I'd have b minus a divided by 2. If I wanted n rectangles, it'd be b minus a divided by n. So this is the general structure of what we are dealing with. We're going to take a video just to explain that. We're going to jump into some examples in just a minute.